In my last note, I introduced you to the concept of diagonalization. And one of the few things that I mentioned are eigenvalues and eigenvectors. So briefly, what are these two? Now, if you have this expression right here, a minus lambda I multiplied by x equals 0. Now, this expression right here tells us that lambda is an eigenvalue of a and x is a corresponding eigenvector. So these two are going to be going hand in hand. Now, for this eigenvalue, how do we compute eigenvalue? Basically, we need to look for the characteristic polynomial of matrix A. And how do we get the characteristic polynomial of matrix A? Of course, there's a formula method which I used in the notes, which says that if you have a 2 by 2 matrix, just like the one we were given, so we had matrix A equals -2, and we have -6, and we have 4 and 8. So it simply says that the characteristic polynomial, so let me call that P, is going to be expressed as lambda squared minus the trace of A, multiplied by lambda, then plus the determinant of A. That's simply what the characteristic polynomial is going to be like. Of course, I could just subtract lambda from each of these and try to multiply it and re-express what I'm going to get. So for instance, what I'm saying is that if you do this A minus lambda I, which is what you are going to find the determinant to get the characteristic polynomial, so you're going to get A minus lambda I is going to be equal something of this nature. Then you have -6, you have 4, and you have 8 minus lambda. Now, when you find the determinant of this particular matrix right here, when you find the determinant, you get the characteristic polynomial. But this expression right here is going to help me get that, so there's no need to do all of this anymore. So let's quickly get the characteristic polynomial, which we are going to be equating to 0. Of course, this is going to be P would be lambda squared. What is the trace of a? Trace of a matrix is simply the addition of all the elements in its principal diagonal. -2 plus 8, that is for this, that is 6. So we have -6 multiplied by lambda a. And what will be the determinant of this 2 by 2 matrix? -2 times 8, that is -16. And we have 4 times -6, that's -24. So -16 minus -24, that is going to be -16 plus 24, which is going to be plus 8 equals 0. So if we solve this particular polynomial very well, this is a quadratic expression. It means that lambda equals 4 or lambda is going to be equal to 2. And these are our eigenvalues. Now, how do we get the eigenvector? All we need to do is to substitute it into this expression. And this is just like simultaneous equation. And if we want to solve it by using the Gauss method, we just need to augment this entire matrix right here. We just need to augment it with 0 and try to solve for it. So one of the things I introduced in that place as well is solving a system of equation that is all completely equal to 0. And how do you solve that kind of system? So let's see. I'm going to compute A minus lambda I for when lambda equals 4, when we have lambda equals 4. So what's that going to be? We'll have, don't forget I said that we'll augment A minus lambda I, we'll augment it with the 0 matrix. So let's see what's that going to be. So that would be A minus, so since we are going to be subtracting just this element, so -2 minus 4, that will be -6, and we have -6 here, we have 4 here, and we have 8 minus 4. So 8 minus 4 is definitely going to be 4 as well. So if I augment these with 0 and 0 right here, so you know the basic aim of these is to make this particular 4 to be 0 as well, so that we can see what we can solve. But you don't really need to waste your time. When you see a matrix like this, the rows are the same. If you're using Gauss method, it means that this last row, the rows are multiples of each other. It simply means that this last row is going to be dependent. It's going to be linearly dependent on the first row. And that means that you can easily wipe out this last row here, and you are left with -6 at the top, which you can also divide through by 1/6, that is if you like. So this is going to give us 1, 1, That's augmented with 0, and we have 0, 0 down here. So if you're familiar with the Gauss Elimination method, which is not the aim of what I want to explain in this particular video, then you know that what I've done here is absolutely correct. So 4, 4. If you want to know how to do the Gauss Elimination method, I'll put the link of a video that I've explained how to use Gauss Elimination method in the link below. So just do well to check that out. Now, so here's where the issue is. How do you find x1 and x2? One thing about eigenvector is that there are several of them. Just that each of these eigenvector that is corresponding to one eigenvalue, they are multiples of each other. That is, they are scalar multiple of each other, which implies that you can get a particular eigenvector, but another person can get a different eigenvector as well. So what do you do? Now, in this place, we have one free variable and we have one pivot element. So in this place, we can say that if this is corresponding to x1 and this is corresponding to x2, we can say let x2 equals k. So if x2 equals k, according to this first equation, that implies that x1 plus k equals 0. And that implies that x1 equals negative k. So if we're going to write that, so x1, which corresponds to, of course, we know that lambda 1 is 4. x1 is going to be x1 x2, which we have gotten right here as negative k and k. So this is, k is any integer, k can be any integer, which will be negative 1, 1 multiplied by k. So we can put k out there. Now, so we don't really need to worry about k. This negative 1 and 1 is our eigenvector that corresponds with lambda 1 equals 4. And that's settled like that. So let's quickly find the second one. When lambda equals 2, we will do our augmented matrix again. Of course, we know that when lambda equals 2, this is still the expression. So we have negative 2 minus 2, that's going to be negative 4. So we have negative 4 and negative 6. Let me put that right here. We have negative 4 and negative 6. And then also we have 4 here. We have 8 minus 2, that's 6. So we have 4 and 6. We have 4 and 6. So as you can see, what you would notice here is that these two rows as well, they are multiples of each other. And just like we did the other time, we can simply cancel this last row out. And then we divide this through by 1 over 4. We'll multiply this through by 1 over 4 or 1 over 6. Whichever one we like to do there. So if we multiply this through, which is going to be, so this is then going to be implying that we have 1 and we have 3 over 2 augmented with 0 right here. This is going to be 0 as well. We only have 2 zeros. Now, so for this now, we have this augmented matrix. So we can say that let x2 equals, now I want to really get rid of this 2 down here. So I can say let x2 equals 2k. I wouldn't be doing anything wrong if I say let x2 equals 2k. So that implies that x1 plus 3 over 2 times 2k would be equal to 0. So which implies that x1 plus, so if 2 cancels out, we're going to be having 3k equals 0. And that implies that x1 equals negative 3k. So finally, we have x1, x2 is going to be equal to, so negative 3 and 2k, negative 3k and 2k. So which is k negative 3 and 2. So now we have the second eigenvector. So for lambda equals 2, the corresponding eigenvector, so which is x2, is going to be negative 3 and 2. So what does that imply? That implies that our matrix P, that we need to diagonalize this particular matrix right here, is negative 1, 1, and negative 3, 2. And what does that imply? The inverse of this matrix the inverse of this matrix. Of course, let's find determinant. Determinant of matrix P is going to be -1 times -2, that's -2, and then minus 1 times -3, that is -3. If you do this very well, it's going to be -2 plus 3, which is going to be 1. And if you do that, so since determinant is 1, we just switch places of these two, and then we change the sign of that. So P inverse is going to be 1 divided by 1, which is still going to be 1, of 2, -1, and we have -1, positive 3. So this is our P and P inverse. Now, to the diagonal matrix. Now, what will the diagonal matrix look like? Diagonal matrix D is actually going to be equal to, now you don't need to stress yourself. Of course, there's an expression like I've given in the notes how you find the diagonal matrix. But what you're going to get at the end of the day is that your lambda 1 is going to be here, and your lambda 2 is going to be here. That is what the diagonal matrix is always going to give you. So you don't need to do that long process of matrix multiplication. So this is just going to be, so what's lambda 1? Lambda 1 is 4, and this is 0, and this is 0, and this is going to be 2, which is lambda 2. And finally, I said that to now do a raised to power n of any matrix, all you need to do is to start with your matrix P, which is, matrix P is -1, -3, 1, 2. Then now this will just be 4 raised to power n, 0, 0, 2 raised to power n, multiplied by the inverse of that matrix. So this is 2, 3, -1, -1 as well. Now, as you can see right here now, so we don't need to do any, so we don't need to start computing the powers of A, like A times A times A times A. Let's say we have n to the power of 6, n to the power of 7. We don't have to do this 7 times. All we just need to do is to raise these two numbers to 7, then whatever result it is, we multiply just these 3 matrices and we get the result, which I've illustrated in the notes using n equals 5. Of course, I didn't use n equals 20 because this would be a very, very, very big number. So if you understand this concept, drop a comment below.